Good day and welcome back for part 2 of our discussion on linear approximations. So the reminder for you is that linear approximation is just a new name that we're given for the equation of a tangent line. For example, if we are asked to find the linear approximation of a function at a value, that is nothing more than just a fancy way of asking us to find the equation of the tangent line to the curve given by y equals f of x at x equals 0. So this initial part of finding the linear approximation, i.e. finding the equation of the tangent line, that really is a familiar question. Whereas the new part of the problem revolves around the idea that this linear approximation, i.e. the tangent line, is going to approximate the function value. So if we look at the specific question that we're starting with, for this function, the cube root of 1 plus x, find the equation of the tangent line at a equals 0, and use it to approximate this number, the cube root of 1.1. And let me give you just a little bit of intuition to the side here. If we are starting with the function, the cube root of 1 plus x, and we want to know a little bit about the cube root of 1.1. Note 1.1 would correspond to substituting 0.1 into our function. And arguably, 0.1 is close to 0, which tells us we can use the linear approximation to get an approximation on this function value. Now, if we think about the cube root of 1.1, roughly we have an idea of what this is going to be. It's something a little bit bigger than 1. But the question is, can we give a better approximation than that and also have some sound reasoning behind it opposed to just our intuition? So what we have is that this is f of 0.1 is approximately equal to L of 0.1. And this gives us our game plan. If we want to approximate this value, the cube root of 1.1, it's really a two-step process. We first need to come up with a linear approximation. That's a familiar part of the problem. Then we evaluate it at 0.1. So let's go through a few steps. Without any work whatsoever, we immediately know the form of our linear approximation. This will be f prime of 0, x minus 0, plus f of 0. And we'll do a couple quick computations to the side. F of x is the cube root of 1 plus x. So f of 0 is the cube root of 1, which is 1. I have written f in a way that it is convenient for us to differentiate. So maybe pause the video and write down what the derivative of f is. Using the chain rule, we think, 1/3 comes down front. The new power is 1 less. We substitute in the inside function and then multiply by the derivative of the inside function. In this case, the derivative of the inside function is 1, so you actually don't need to write anything down. But just to make sure we're not forgetting there's a chain rule going on, I'm going to write that down. And then f prime of 0 is going to be 1/3, 1 to the minus 2/3. And remember, 1 raised to any power is still just 1, so this is going to be the number 1/3. And this completes the first part of the problem for us. The linear approximation at a equals 0 is given by 1/3 x plus 1. Now that we have this linear approximation, let's see if we can move on to part 2 and approximate the cube root of 1.1. A very important part of this problem is kind of connecting your work together. And what I'm going to need you to do is somehow show me that you've thought about the function value in relation to this linear approximation. So what I would want to see in this example is something like we have to the side. The cube root of 1.1 is f of 0.1, which is approximately equal to the linear approximation at point 1. And that's really what I'm looking to see in the problem. But if you also wanted to add in there a little bit of explanation, you could simply say because point 1 is close to 0, which means the linear approximation is going to approximate the function value. So let's go ahead and just substitute that in. If x is 0.1, we would have 1/3 times 0.1 plus 1. And what I will ask you to do, and what we'll see kind of in our next example, is I want your approximation as a decimal. So let's go ahead and just do a little bit of arithmetic and kind of simplify this down. So in this case, I'm going to reorder the terms and say we have 1 plus, and let's think about this as a decimal. 1/3 would really be 0.333, and I'll just put a little bar over it to say it's repeating indefinitely. And then we're multiplying that by 0.1, so think 1/10. And what that's going to do is slide the decimal place 1 over to the left. So this would be 1 plus 0.03 repeating, which is equal to 1.03 repeating. And what we've learned is that the cube root of 1.1 is, yes, a little bit bigger than 1, and we're going to approximate its value as being about 1.03 repeating. And just to reiterate, this is a very common example involving linear approximations and using them to approximate a function value. In order to come up with this approximation, we need it to somehow have an associated function and a corresponding number, in this case 0, where the function is easy to evaluate and clearly connects back to this cube root of 1.1. So let's look at maybe a slightly more involved version of this first example. And I say slightly more involved because all we are going to do in this second example is ask you to approximate a value. And the fun part of this problem is it leaves a bit more to you. That is, you need to come up with this function and associated linear approximation that will help us approximate the square root of 99.8. So a few ideas to kind of get us going. So one thing is that if we want to model off our previous approach, we need a function to use. So you have to determine a function. So let me note that furthermore, you want it somehow to be related to this square root of 99.8, and you're trying to think of some value that's really easy to compute off the top of your head that's close to the square root of 99.8. And hopefully you're thinking the square root of 100 is 10. And with this in mind, we could maybe come up with the function that we want to define, and there's many different ways that you can come up with the function. So I'm going to, in this example, say, how about we use f of x equals the square root of 100 plus x, and what we would like to do is find the linear approximation at a equals 0 and use it to approximate that desired value of the square root of 99.8. So I'm going to suggest that you pause the video and give yourself 4 or 5 minutes and see if you can come up with this linear approximation and use it to approximate the function value. And hopefully at this point you've paused the video, you've put a little bit of thought into this. And I do want to reiterate the fact that this is not the only function you could have used, and I'll note a few other functions you could have used in a moment after we finish up this work. So we want to find the linear approximation at a equals 0. So that's going to be f prime of 0 times x minus 0 plus f of 0. And if f of x is the square root of 100 plus x, f of 0 would be the square root of 100, which is 10. It's this easy value for us to compute. f prime of x, differentiating this using, think, the chain rule in combination with the power rule, we would have 1/2 100 plus x to the minus 1/2, and then times 1, the derivative of that inside function. So really that's 1 over 2 square roots of 100 plus x. So f prime of 0 is 1 over 2 square roots of 100 plus 0, which is the number 1 over 20. And putting this all together, we now have the desired linear approximation. L of x is equal to 1 over 20x plus 10. And this is a linear approximation to the function the square root of 100 plus x at a equals 0. And now for the really important and new part of this problem, somehow we need to use it to approximate 99.8, and we very clearly want to connect our work together in a way that justifies what we have done. So this is equal to the function evaluated at minus 0.2. And because minus 0.2 is arguably close to 0, this is approximated by L of minus 0.2. That is, substituting minus 0.2 into our above equation for the linear approximation. And if we do that, we would have 1 over 20 times minus 0.2 plus 10. And note, minus 0.2 divided by 20, this is going to be minus 0.01 plus 10. And our approximation is 10 minus 0.01, which is 9.99 as a single decimal. And I do want to go back to our starting point for the problem where we had to come up with a function to use. Let me just note a few other functions you could have used. So instead, you could have let g of x be the square root of 100 minus x, and you would still find the linear approximation at a equals 0. The only difference being, instead of having to substitute in minus 0.2 to get to the 99.8, you would substitute in positive 0.2. But that negative would be accounted for when you differentiate and you use the chain rule. Or, you certainly could have just used something like, say, h of x is the square root of x, and you could find the linear approximation at a equals 100. So there are, in fact, many different possibilities, and I would encourage you to think about how the computations would work in one of these other cases. So with that, we have finished up the material not only for this video, but for the topic of linear approximations. I highly recommend, as usual, that you go through, work some of the suggested problems, reach out, let me know if you have questions. And as you read through the section, you'll probably notice a discussion on things called differentials. For the moment, I choose to skip past them, but later on, as we run into them and need them, I will introduce the definitions and discuss the importance as needed. So as usual, stay tuned and take care.